Yes, hello everyone. Welcome to this first Async webinar. We'll hopefully be running more in this series. If you just bear with us a couple of minutes, just to give the latecomers an opportunity to dial in, we'll begin in a couple of minutes.
There's
quite a few people just popping in now.
Yes. Great to see so many people from all over the world joining us. I don't know what the time difference is where everyone is attending from.
It looks like we've pretty much covered most time zones here.
I think so.
Yeah, thanks for your patience, guys. A couple of minutes. You can hear those beeps in the background. That's people, latecomers signing in. Okay. I think we can, a couple of minutes in, we can start. So, welcome everyone. As I said, welcome to this first of hopefully a series of webinars that we're going to be giving at Asyntsa, covering various topics. Today, we're going to be running a introduction to flow chemistry. Now, this is really designed for beginners, for people that aren't familiar with flow chemistry. I'm not going to go into anything advanced because we can cover those in later sessions. And if there's any topics that you'd like us to cover, please get in touch and let us know. Asyntsa's portfolio of products is pretty wide. We can cover everything from flow chemistry, which is what we're doing today, to large jacketed reactors, electrochemistry, photochemistry, whatever you want. We've got most things covered. But as I said, today we're going to be giving you a brief introduction to flow chemistry, starting at the basics, which is probably a healthy place for everyone to start. And then we'll be covering more advanced sessions as we move on. So just bear with me a second. I'm just going to pull up my slide deck. Okay, that will take a couple of seconds just to catch itself up. Okay, hopefully everyone can see that. Excellent. I've got a nod from my glamorous assistant next to me. So yeah, as I said, today we're going to be giving you a brief introduction to flow chemistry. So I'm just hoping these slides catch up. Okay. They are on a bit of a go slow. Have a brief technical hitch with my, there we go. Right, so apologies, my cursor in the wrong position. So yeah, I always like to start off by saying that we're all chemists, hopefully, and we've been in different laboratories over our years as being chemists. I mean, I've travelled to lots of different countries, haven't seen much of them, but I've been into lots of laboratories, and they all look the same. Roughly, we've got fume hoods and we've got the apparatus to carry out our chemistry. But if we go back hundreds of years, the slide next to this, or the image next to this, is from about 300 years ago. And you can see that all of those tools that we use to perform chemistry, those traditional tools, they've been available to us for a long time. If you look at this old image here, we've got round bottom flasks, we've got evaporation, We've got photochemistry, so there's a lens there focusing light onto a reaction. And if you look on the right-hand side, there's even like a parallel station for multiple reactors. So all of these techniques, they're all familiar to us. And if you transpose that to the inside of a modern chemistry fume hood, you can see all of those tools they're roughly the same. With a few tweaks. I mean, we've got waterless condensers now, for example, and we've got oilless baths. We've adapted these things to make them more sustainable. But the tools they're the same. Flow chemistry is slightly different. We're using different tools, but we're using those tools to perform the same chemistry. So I always start off right at the top by saying flow chemistry is just another synthetic method for us. It's another technique to carry out our chemistry, and it's complementary to those traditional methods that we're all familiar with. So combining the best technique for the right chemistry, whether that's traditional batch techniques or flow chemistry techniques, we can get the best of both worlds and we can get the benefits of both. But flow chemistry is simply, at its basic level, a tool for allowing us to control our reaction parameters more precisely, whether that's mixing, molar ratios, time, temperature, all of those useful parameters that enable us to be more selective in our chemistry to get the desired outcome. And if we can control all of those factors, it gives us lots of benefits and opens up a wide range of applications. So let's start off at the basics. So we all know how to perform traditional batch chemistry. We have either a round bottom flask or a jacketed reactor. We load our reagents in, we heat and cool them. We can even shine a light on them to do photochemistry. So we're using photons of the reagent, or we can use a pair of electrodes, put a potential across our reaction, and use electrons for electrochemistry. So there's lots of different methods of activating our chemistry. So we heat and cool or activate for chemically whatever for a period of time. Then we need to take our reaction mixture from our vessel, we evaporate, we work up, we isolate our desired products. So there's a number of discrete steps there. And we're thinking about reaction parameters like time, temperature, molar ratios, mixing, and concentrations. All of those kind of key control factors that allow us to get the best outcome from our chemistry. Now, flow chemistry is slightly different. Although we're performing the same chemistry, we're doing it in a different manner. We're just using different apparatus. So we have solutions of our starting materials, our reactants and reagents. We pump those into some kind of fluidic channel. They mix and then pass through a flow reactor, some kind of capillary. And we can heat and cool, and we can even carry out photochemistry and electrochemistry continuously. And they're continuously pumped, our reagents are continuously pumped, they continuously react, and they elute. So that's the flow part of flow chemistry. So when we think about those chemistry parameters, those experimental parameters, we're still thinking about the same things. So we're thinking about time, temperature, molar ratios, stoichiometry. We're thinking about mixing. But now we can add pressure as another consideration into a flow chemistry experiment. And we'll cover that as we go through this introduction session this morning. So let's look at that in a little bit more detail. So in a flow chemistry experiment, we need to have our input reagent streams. So in this diagram here, I've got A and B. So a simple two-component reaction. And these are ideally in solution. So we'll know their concentration. Now we need some kind of pump to introduce our reagents, and we can control the flow rate of those pumps. So we can control the flow rate of A and B. And if we know the concentrations, we can quite precisely control the molar ratio of those reagents flowing into our system. So we pump our reagents, and then we need to mix them. So they'll come together at some kind of mixing junction. Typically, this is just a simple T-piece. and our mixing regime will be under laminar flow conditions typically, but we can add turbulent mixing in there for those reactions that need fast mass transfer, those very fast exothermic reactions. And then they pass along our temperature controls flow reactor, and they're continuously eluted. So we know at concentrations, and we know the pumping speeds of our inputs, so we can control the molar ratios precisely. Mixing is always constant, so we're controlling the mixing regime. And then we can control how much material we're passing through the reactor. So we can control the throughput. If we know the volume of the reactor, and we'll cover that next, we can control how much time our reagent spends in that heated environment, heated, cooled, irradiated, whatever environment. So we can control that reaction time precisely as well. We'll cover controlling reaction temperature, but we can control reaction temperature a lot more precisely because we're using a capillary, and we'll talk about that in a little detail in a second. So you can see just from that simple diagram here, that simple illustration with a simple A plus B system, we're already showing better control of our reaction conditions, and that would be one of the simplest methods for a flow chemistry experiment. One reactor, A plus B. But I guess you could sit back and think philosophically, we've got these tools that we've been using to carry out chemistry for years. Why would we want to change? Why would we want to invest in new apparatus to carry out chemistry? Well, there are lots of benefits, and I've highlighted some of them here. Not all of them, but some of the pertinent ones. So we can potentially increase the reaction time of our reactions. We can have faster reactions. We can increase safety, so we can potentially reduce the associated hazards with our chemistry, and we will touch on that. We're already talking about increasing selectivity, so we can control the outcome of our reaction in more precision. So it's easier to scale, and that will become apparent. It's a continuous process, so we can optimize on those milligram scales where we're only interested in data, and then we can use the same system to flow for longer, to put more reagents into our experiment and produce more material. And then we can also add automation into that process. We can automate the inputs of our reagents, so we can look at reagent screening, for example. We can automate series of reactions to explore different reaction parameters when we're optimizing or developing methodology. And we can have those in a completely walk-away process with automated collection as well. And then we can add those principles of automation to make small arrays of material, of compounds of interest. If we're looking at early drug discovery process, for example, when we want to make lots of analogues, we can automate that process where we take the concepts of optimization, where we have varied our reaction parameters to find the ideal. And then instead of exploring the reagent screening with an automated sampler, we can have a series of monomers to build up around different scaffolds to build a library of compounds to increase that chemical space and increase diversity. And then we can also add things like integrated inline analysis. So we can continually monitor each of our reactions. And these generally have a flow cell. So if we're looking at optimization or looking at library synthesis, for example, in an automated process, we can interrogate, we can see exactly what's going on in each of those reactions. And I guess the integration of analysis with the kind of concepts from academia coming through at the moment with machine learning, closed loop optimization type applications, this is really key. And we can offer that at Asynt as well. And I put sustainability in here because flow chemistry also touches on quite a few of the green chemistry principles. And I put a couple here. So increased atom efficiency, that comes from having better selectivity, solvent reduction, reducing hazards, and there are many more. And I would say that all of these benefits don't appear in isolation. They're generally in a combination. So flow chemistry can offer quite a lot to us when we're performing our chemistry. It can't do everything, which we'll cover later, but what it can do often gives benefits. And if you look at chemical literature, you'll often see comparisons between batch and flow experiments, and flow will give us some kind of advantage. So let's look at that idea of selectivity again. So in our chemical reaction, if we have variation in our reaction conditions, that can give rise to unwanted side reactions. You know, our process isn't performing optimally. And if we have variation from batch to batch, then we have various varying outcomes of the product yield, for example. So unwanted side reactions, formation of byproducts and lower yields gives rise to increased workup and isolation. So all of these things need to be taken into consideration. So those parameters that we spoke about earlier, temperature, mixing, addition, reaction time, molar ratios and concentrations all play a part, and we can control those in a little bit more detail. So let's take just a step back and think about that concept of controlling reaction time. Now, in flow chemistry, we call that the residence time. And that's the time that every part of our reaction spends in our flow reactor. So we were talking about having a flow reactor of a discrete volume, of a set volume, and it's every part of our reaction that spends in that heated, cooled, irradiated environment. So this is analogous to the reaction time. But you can see as we're flowing out, we can stop our reaction at any time with inline quenching, for example, or if it's thermally mediated, as soon as we leave that heated environment, our reaction will stop. So residence time is one of those key principles, and it's really simple. We have a reactor, flow reactor, whether that's a capillary, whether it's a glass chip with a channel etched in, packed bed reactor, for example, it's a fixed volume. And we have pumps, so we can control the flow rate. So the residence time is a simple calculation. It's the reactor volume divided by the flow rate. Now, if we can control the pumps, we can control the time in the reactor, we can vary those flow rates, and then we can control the molar ratios precisely as well. So those reactions where you need precise one-to-one molar ratios in things like reduction, where if you have an excess of the reductant, you can lead to over-reduction. We can control those types of reactions very precisely with very precise stoichiometry control. If we think about mixing and addition, batch reactors can give us concentration gradients, which give us those unwanted reaction pathways. So if you think about mixing, when we're mixing in a round bottom flask or a jacketed reactor, that mixing is chaotic, it's turbulent. It's never the same, and that can give rise to batch variations. Now, we can increase that mixing efficiency by having baffles and changing the geometry of the reactions and the impellers, for example. But you can see from that simple diagram here that that's never going to be the same from one reaction to the next. It's chaotic. It's turbulent mixing. Now, I've taken the timestamps off of this image because that can be quite quick, but some reactions are very quick, and you need precise, very efficient mass transfer to get the optimum conditions from our reaction. So that's mixing. If we think about addition as well, the most precise method that we have under batch conditions for adding our reagents is dropwise addition. And you can see from this diagram here, even with that precise control, we have a concentration gradient of A to B, and that can give us variations in our reaction conditions as well. It gives us those concentration gradients, and it can also give us back mixing because our products will see excessive reagents, for example. In flow chemistry, as I said, when we get to that mixing junction, we can even mix under laminar flow conditions or turbulent conditions as we did in batch. Laminar flow conditions are continuous. They are reproducible. It gives us exactly the same mixing regime from batch to batch. And you can see from that diagram there that under laminar flow conditions, we're not mixing immediately, it's mixing by diffusion. So that's laminar flow. So that mixing is constant, which means it's reproducible. And as our reagents and our reactions been carried out along that capillary, our product doesn't see any excess of reagents unless we want it to. So that eliminates back mixing as well, and eliminates those concentration gradients. So you can see that's given us a little bit more control. So we have increased control of our reactions, and we can control the reaction pathway. So, as we've said before, less byproducts, less workup, increased yields. So, as I said, we can have turbulent mixing in flow reactors. And as I said, some of those chemistries, those fast exothermic chemistries where we need really efficient mixing, mass transfer, as well as temperature control, can be carried out. So we typically use something called a static mixer, and you can see this diagram here in this image of one of our Unixis static mixers with orange channels highlighted. So this is a glass plate with a serpentine channel etched in, but the chicane geometry is in here, means that our reagent streams are continuously mixed all the way through that reactor. So we have precise control of mixing, or fast control of mixing, as well as temperature control. So that's mixing in additions. If we think about temperature, when we're heating our round bottom flask or a jacketed reactor, we're heating from the outside in. Now, with small round bottom flasks, that's pretty easy to do. It's a small volume, so getting to the desired homogeneous temperatures is pretty quick. But if we start to scale up our reactions and have larger reactions, because we're heating from the outside in, that can give rise to temperature gradients. I mean, we will get to a homogeneous temperature eventually, but that can give rise to unwanted reaction pathways with different activation temperature, different activation energies. If you look at the diagram here, you can see as we're applying heat, it's taken a while to get to that desired temperature. And we take the heat away, and that temperature takes a while to get back to ambient. And that's analogous to cooling as well, because we're only being able to take that heat if we have a reaction that's exothermic and we're generating heat. We can only diffuse that heat, take that heat out, but from the outside. And if we have exothermic reactions, sometimes they're very difficult to control under traditional batch methods. If we think about a flow reactor, as I said, that's typically a length of tubing that can be constructed in any material, perfluoroelastomer, stainless steel Hastelloy or whatever, or a glass plate with a channel etched in. There's a really high surface area to volume ratio. That means we've got a very high surface area along our reactor compared with a batch reactor. So we can add energy in, we can add heat in, but it also allows us to dissipate heat very effectively as well. And if you look at that cartoon of heating a flow reactor, as soon as our reagents come into that heated or cooled environment, they're almost immediately at the reaction temperature. And when we're cooling, we can control and dissipate that heat very effectively. So exothermic reactions we can carry out, but to degrees of our set temperature. And when our reagents leave that heated environment, they're cooled almost immediately. So we can control that heating and cooling regime as well. And if we take that to things like electrochemistry and photochemistry, we can precisely control that radiation or exposure to our electrochemistry conditions. So as soon as our reagents are loose, the reaction will stop if it's mediated in that fashion. So really good temperature control in a flow chemistry system. So that's heating and mixing and additions, controlling stoichiometry. They're all of those kind of continuous reaction parameters that we can control, and we can automate those very efficiently as well. Adding autosamplers will enable us to look at discontinuous variables, so solvent screening, whether that's a catalyst or an enzyme or reagents or whatever. So I'm going to cover a couple of the benefits And one of them I said was potentially increasing our reaction rates. So if we think about a ramp flask or a jacketed reactor, we're limited to the reflux temperature. We can have condensers, which will allow us to operate at that reflux temperature. Unless we have a sealed reaction vessel, stainless steel bomb, for example, we can't exceed that. And we're taking all of our reaction components into consideration as well. If we're using an organic base, for example, we need to take into account the boiling point of that. But that can lead to longer reaction times because we physically can't heat it any higher. And if we try to scale that up as well, we need bigger, more expensive stainless steel pressured reactors. In a flow reactor, we're typically looking at smaller volumes. We'd be looking at, tens on a lab scale, tens of milliliters. So that means they're really easy to pressurize. We can add a back pressure regulator, much as we would do with a HPLC system, and we can pressurize that environment. And if we can pressurize the environment, we can take our reaction mixture above its reflux temperature. It enables higher temperatures. If we get higher temperatures, we can increase the activation energy and hopefully reduce reaction times. So I know this is pretty small in here. I should have made that a little bit bigger. But we all know water at atmospheric pressure boils at 100 degrees. That's a constant. We're taught that from year 1 at school. If we increase the pressure, and I've only taken this up to 17 bar, we can more than double the boiling point of water. And we can apply that to other solvents in our reactions, but also take into account the other volatiles within our reaction. So the Asynt range of products, and this isn't a sales pitch at all, but we can operate up to hundreds of bars of pressure. So if you take that into account, we can increase the reaction temperature to very high levels. Pressurizing also allows us to access continuous gas reactions, whether that's using the reagent gas or whether that's performing chemistry that evolves gas with those kind of rearrangement chemistries, Curtis and Schmitz and things. But we're talking about heating reactions here. So I'm not going to go into the physics of the Arrhenius rate law, but essentially what it says is for every 10 degrees in reaction temperature increase we can access, that will halve reaction rates. So reactions that take hours, we can get down to tens of minutes, hours to minutes, tens of minutes to minutes, minutes to seconds. So we can intensify our process if our reactions are thermodynamically mediated, if it's activated by heat. So we can potentially reduce those reaction rates. And if we can reduce those reaction rates, then we can create more material. We can flow faster through the same volume flow reactor and have a higher throughput. So that's a really good application for, or example of process intensification, which is green. So we can increase reaction rates, we can reduce reaction times, and we can increase throughputs. So that's increasing reaction rates. Why is it easier to scale up? And I guess this is just one of the most obvious examples of flow chemistry. If we're looking to scale up a batch reactor, we either increase the size of the reactor or we run multiple reactions to increase the amount of material we produce. The bigger the vessel we have, the more temperature control we need to have. So typically when you're looking at multiple litre volume reactors, they're typically jacketed, so we can control the temperature a bit more efficiently. So we need to take into account cooling as well. So as they increase, it becomes harder for us to control the reaction temperature. We need to think about the control of addition and mixing as well. And if we're working on a 50 milliliter reaction, adding our reagents don't take that much time. But if you're looking at 10 litres or 50 litres, that addition rate of controlling the addition of our reagents takes a lot longer. And all of those things need to be taken into account. And then we need to think about the different stages of optimization. Going from reaction scale and increasing, often involving reoptimization. So we need to look at our reaction conditions again and optimize our conditions. And all of that takes time, effort, money, investment in larger reactors, all of those things that are detrimental to scaling up some chemistries. So with a flow reactor, we can just leave everything running. And one of the analogies that I like to use is, so you've got a hot and cold tap, and you can adjust the temperatures to get to the inputs of hot and cold to get to the right temperature, and then you can fill a cup, or you can leave it running and you can fill a bath. If you've got time, you could fill a swimming pool. If we take into consideration that principle of residence time that we spoke about right at the beginning, if we increase the reactor volume, we can increase the flow rate and have exactly the same residence time. So we can scale up from the same system. So we can, as I said, we can optimize on milligrams and then produce tens, hundreds of grams per hour. But if we wanted to get into that kind of kilogram, multi-kilogram, that kind of production environment with throughputs, then we need larger reactors. And then that does need some re-optimization because we're using different systems. So for laboratory scales, which is where we operate, we're looking at producing from milligrams to tens, hundreds of grams per hour, depending on the chemistry, so the reaction time and the concentration, potentially achieving kilograms per day with the right chemistries, with exactly the same system that we optimized our methodologies on. And then we're looking at those kind of like pilots and manufacturing scales. We're looking at kilograms or multiple kilograms. And there are lots of API manufacturing occurring at the moment where continuous manufacturing is becoming more of the norm. But that can be applied across most chemical industries. So I've said here, how can flow chemistry achieve reaction conditions not possible in batch? Now that is quite a bold statement. We can't do everything in batch, but what we can do is use those flow conditions to access methodologies that would be difficult to achieve. So we haven't touched on any of the really higher level applications where we can take one flow reactor and flow it into the second or third with varying input streams to have telescoped reactions. But if we take that principle, we can do things like create highly reactive intermediates without any isolation. So we can make those materials that would have a low shelf life or that are difficult to find, or starter materials that are just not apparent in fine chemical catalogs. So we can create those reactive intermediates without any isolation, flow it into a secondary reactor with another substrate. Now, that simple two-component or two-reaction system is really easy steps to transition from that A plus B one reactor. That's difficult to do under batch conditions. We can take that idea and generate hazardous reagents in situ. So we can create reagents that we wouldn't want to handle in small amounts, react them without any isolation, and then quench the excess on the outstream of our reaction. So we can produce things like hydrogen cyanide or diazomethane or any of those really nasty reagents that we wouldn't want to handle. Saves us having big feedstocks of those flowing into a flow system. We can create them in situ, use them, and then kill them. We can use that idea of accessing all of these different chemistries that we can get benefits from to create diversity, whether that's in our starter materials. As I said, we can create material that isn't readily available, that will give us advances or benefits over our competition. So I know, for example, there are lots of heteroaromatic halides, but there aren't a wide range of heteroaromatic boronic acids. That's a simple step in flow. We can make those on demand. And then we can use that to increase the chemical space. And if we're using automated reagent injectors, then we can create that diversity as well by doing creating libraries. We can scale pressurized reactions, and that's a pretty big one. You know, we can then now have continuous processes for things like oxidations or carbonylations or even hydrogenations, which would be difficult to do without large pressurized reactions. These gas reactions not only take into account the addition of reagent gas or reactive gases, but also in the evolution of gas. So if you're doing a large-scale Curtius, the evolution of the gas within that would be difficult to contain on scales. I mean, it can be done, but in a flow reactor, because we're pressurized and we're only reacting a small amount of material at any point, that evolution of gas is controlled. And then we can control the outgassing at the other end. So all of this kind of comes down to increased safety, increased selectivity, increasing chemical space, and highlights and adds to some of those benefits that we've spoken about. So just to kind of, as we're coming towards the end of the kind of presented session here, I'm just going to highlight some of the chemistries that we can carry out under flow conditions. So the ideal for flow chemistry is everything being in solution. It's easier to pump solutions than it is other materials. So we want our start materials in solution and we want our products in solution as well. That's the ideal, having a monophasic reaction condition. Accessing biphasic conditions is another advantage, and we can do that. So we can have an organic, inorganic type setup. What we often see, if we're controlling the geometry of our reactor and the flow rates, that we can have very small partitions between those two phases, and that increases the surface area. And there are some examples where those biphasic mixtures under flow conditions have removed phase transfer catalysts, for example. So we have a very high surface interaction, which is a benefit. Now, one of the downsides of flow chemistry is it's very difficult to pump solids. So solids material in going through a pump is difficult to handle. You know, I'm not gonna lie about that. If our suspension or emulsion or slurry is stable, then we can pump those a bit easier if we're using the surfactant, for example. But it is just tricky to pump high solids to liquid ratios. What we can do when we want to use solids is use a packed bed reactor. So there's an example here with a glass column with our reactant immobilized or packed within that environment. So we call that a column reactor or a solid phase reactor, but typically it's called a packed bed reactor. So we can fill that column, whether it's glass or stainless steel, for different temperatures and pressures, with our reagents, whether they are solid or immobilized, our solid catalyst or enzymes, and we flow our substrates over the flow, and we have a surface interaction. So that's how we get around high solid content. Then we can have gas liquid partitions. So we can have that same biphasic condition where we have two immiscible liquids, but we can have that with gas and liquid. And then we can combine all three to have triphasic systems. So we can carry out most chemistry, but going back to what I said about batch and flow being complementary, if we have a high solid content that's not going to dissolve in our reaction, for example, batch is always going to be king. It's always going to be the preferred method. If we can't increase the reaction time of our reaction under flow conditions by mixing or temperature, for example, and we have very long reaction times, batch will always be better. So we have to weigh up what technique we're using, whether it's batch or flow. And having the ability to choose between two gives us as chemists the best tools to carry out whatever application in chemistry we want to carry out. And I'm just going to finish off by saying, I mean, what do you need for a flow chemistry system? Not a lot is the answer. So if we go back to that simple A plus B and one reactor system that we were talking about right at the very top, we need 2 pumps. So the pump is arguably the heart of the system. If we don't have confidence in the precision and performance of the pumps, a lot of the aspects that we've been talking about just disappear. So we need a pump that's high precision. We need a wide range of flow rates, and we need really good chemical compatibility. We want to be able to pump that wide range of chemistries that we want to perform. We don't want to be limited by the pump. And we can have pumps in stainless steel or ceramic lined or hastelloy even. So we have the pump, and then we need the flow reactor. And they come in lots of different flavors, for want of a better word. They can either be a tube, as we've spoken about, a glass reactor or glass static mixer with a serpentine channel etched in. Now, they're really easy to change the geometries of. We can have column reactors, or we can use things like CSTR. So CSTR, and there's an image of a small one at the bottom there, is a continuously stirred tank reactor. And it's a kind of a batch flow hybrid. They'll allow you to access chemistries that produce solids to a certain extent. So it's that we'll cover those in more detail later. So what do we want from a flow reactor? It needs wide range of volumes, so we can control the residence times or access to different volumes, and it needs that high chemical compatibility. So that's about it. We need a pump and a flow reactor, and then we can carry out simple chemistry. Now, if we want to access some of those higher level benefits, then we need to be able to pressurize the system. And then we'd add a back pressure regulator. And the example that I've shown there is a simple off-the-shelf HPLC-like back pressure regulator. And that will allow us to pressurize, and they come in different pressure ratings, so you can control what pressure you're adding in. It is very basic level, and then that will allow you to access those chemistries where you want to take reactions over reflux temperatures or start using gases. So a really simple system: pump, flow reactor, back pressure regulator. And then we can add some of those advanced functions, those really nice to have functions. We can combine multiple pumps and multiple reactors. We can add auto samplers, and we can add fraction collectors and automation software, so we can automate the entire process. We can add inline reaction analytics, so we can get some really complex flow chemistry systems. And I think the most number of steps I've seen in cascaded or telescoped is 7 or 8, and that was really early natural product synthesis. I'm not suggesting that anyone goes in and does an 8-step synthesis, but it's achievable without any isolation in between. So you can see it can get quite complex, but those simple 1, 2, 3-step reactions with a little bit of optimization are accessible. So I'm going to finish there, and just to summarize, flow chemistry is a useful technique. It's a really useful tool that can give us a number of benefits over traditional batch methods. So here at Asynt, we can offer you a complete range of flow chemistry products for most applications. We've got the expertise in-house to help you with that. So if you've got any questions, or you want to find out a little bit more about flow chemistry, drop us a line. We can discuss your applications and your chemistry and your requirements and needs, and we can take that further. So just wanted to say thanking everyone that's turned up, and there's quite a number of people there. So hopefully, as an introduction, this has been worthwhile. Watch this space for more webinars coming. And I said, if there's anything in particular you want to hear, drop us a line. So I'm going to open the floor now. If anyone's got any questions, I'm just going to stop these slides.
We do have a couple of questions in the Q&A waiting for us, Andrew.
Yeah, go ahead.
So there's a question from Anna. which could be a basic equipment to perform flow chemistry. When I tried to implement flow chemistry for the lab, I always had to give a description of the reaction I was planning, but I would like a flexible system that we could implement step by step.
Okay, well, I guess if we don't need to know all of the details. I mean, we can sign CDAs if you want, or NDAs. But it's just those reaction conditions that are interesting. Is it homogeneous? What temperatures, what pressures do you want to achieve? If you want to do a multi-step synthesis, then we discuss all of those parameters of interest. So what temperatures, what scales, and we can help you design a flow chemistry system. So this is a consultative process. We give you the right equipment for your application. So we have a range of different pumps, we have a range of different flow reactors, we can control temperature, whether that's low temperatures, cryogenic temperatures, or very high temperatures. With some modification, we can even go to 300 degrees if you want. We have methods of continuous photochemistry, for example. So it's a discussion. All of the Asynt and the Uniquesys products that we have here, sold by Asynt, are all modular, which means that you can start from a very small system, really simple system, to start exploring flow chemistry, and then you can build up the complexity as your needs and experience kind of denote. Hopefully that answers.
Thanks. Okay, so we have a question from Michael. At the moment, flow chemistry is barely taught in undergraduate chemistry education. How do you think flow could be better incorporated into university curriculums to improve students' awareness of the technique?
That's an interesting one. So flow chemistry as a taught subject, as a modular kind of lecture-based subject, is becoming a bit more prominent. There are lots of universities that are teaching the principles of flow chemistry, but you really need that hands-on experience. What you need to do, what we need to take into account, is if you've got a teaching lab of 30 students, you need accessible, cost-effective, affordable flow chemistry equipment. Now, we can do everything from very complicated machine integratable flow reactors to really simple CSTRs, which I showed you earlier, where we just need a very cost-effective syringe pump, you need a flow reactor, and then you need some experimentation to go with that. So we are developing some of those taught experiments that show variation in chemistries to get various outcomes. But yeah, sorry, I'm diversing. What you really need to increase teaching in flow chemistry, as well as the taught subjects, is access for many students to have a piece of apparatus, and that doesn't have to be complicated. So having affordable entry-level flow chemistry, I think that's the key. And we can do that, and we're exploring avenues to try and increase teaching labs to adopt flow chemistry. And if that's something of interest to you, drop me a line and we can discuss further.
Fantastic. So there's been one other comment in the Q&A, just asking about a recording of today's session, as one of our visitors has found it really useful. So just to let everybody know that you will receive a link to the recording of this on Asynt's YouTube channel, probably in a day or two, once we've got it downloaded, uploaded, etc. So we will include information from the questions that have been asked alongside that. Okay, so we've just heard another question from Stefano, saying thank you for the webinar. You're very welcome. What are the limitations to implementing flow chemistry into GMP production, please?
With GMP can be defined in a number of levels. It's generally the process. The equipment, what you need for GMP for the equipment is a kind of cradle to grave so I'm trying to think of the right phrase. You need to have visibility of all the materials of construction and how it's constructed. That's generally what you need from a manufacturer of flow chemistry equipment. The whole process is a different matter. Now, I know that the FDA is lowering or giving assistance for GMP production in lots of different applications, which is kind of warranted, and you can see the rise in API manufacturing. If you've got a GMP process, we don't have GMP certification at the moment, but we can discuss that. We do have all of the access to our base materials for assembly of all of our materials, so it's something we might be able to implicate for you. But yeah, just drop us a line and we can discuss that a bit further.
Brilliant, thank you. So we have a question from Alex. Pumping solids is difficult, but if the reaction produces a solid, is that as much of an issue? Also, can you control a crystallization as well as in batch?
Yeah, that is easier. I mean, you can, if it's a light slurry, light suspensions, to say that doesn't need constant agitation, there are methods of pumping those, but it's not the ideal. I would always probably favour batch. Just because you can do something doesn't mean it's the right method to do it. For continuous crystallizations, you'll often see people using continuously stirred tank reactors and having a cascade of those. And then you can control the addition of your anti-solvent. So if you look at institutes like CMAC as part of Strathclyde, CMAC is continuous manufacturing and crystallization. People have been doing that for quite a while. But having access to creating solids post-pumping is a lot easier. If you've got agitation or you have those CSTR type reactions, the only limitation would be back pressure. But if you're doing a continuous crystallization, you won't have that. You won't have that requirement to add on. So yeah, it is possible. CSTRs are probably the best methods for accessing continuous chemistry methods that produce solids.
Okay, great, thank you. So we have a question from Omkar. Apologies if I've pronounced your name incorrectly. Can we use flow chemistry for, and I'm probably going to pronounce this wrong as well, esterification reaction?
Yeah.
As continuous removal of water is necessary in this reaction.
Oh, okay. I was going to say esterifications should be pretty straightforward. We've got access to strong acids and bases, so that kind of acid base esterification method is doable. Azeotroping is difficult because we're pumping through a capillary, so we can't take that water out. I have seen methods where people have used drying reagents, so running reactions through a packed bed of some kind of dehydrating reagent. You can have permeable membranes that will allow you to separate organics and inorganics. I haven't seen that developed too much for azeotropin reactions or continuous distillation. So yeah, that is a problem of taking unwanted water out, but it depends on the chemistry. Because we're continuously pumping, the amount of water that you produce is directly proportional to A plus B. You don't see an excess of water build up, so that does help in certain applications for esterification. If you take your reactions way above to high elevated temperatures, then you can do uncatalyzed esterifications. And there's some example where people have been running at 260 degrees without any issues. And just using the alcohol solvent.
Okay, fantastic. We have another question. Why flow chemistry is not applicable for bulk scale up in batches?
Why is it not applicable for? I would say it is.
Yeah.
So it depends how long you want to run your campaign for. There was a paper from GSK a couple of years ago, and they only produce 1.5 kg, but they did that in 6 steps. And I think that was just probably for the working day. So it is applicable for scaling up in batches. And all of those benefits we spoke about, if you've made the solutions up in the right concentration, that batch to batch variation should be lessened as well. So I would say it is, yeah.
Okay, fantastic. Another question, the last one at the moment. So if anybody else has anything, do pop it in the Q&A box. Dreos asks, please could you comment on the advantages and disadvantages of using cascade flow reactors in comparison with the classic coil reactor? That's an interesting one.
Yeah, I mean, you're talking about getting to a kind of plug flow regime. The residence time distribution, and I'm going to go into kind of fluid dynamics and those types of equations, is when you're using a cascade of reactions. So if we're talking about CSTRs, you need at least, I would say, 5 of those in series to get your residence time distribution comparable to a batch reactor, to a typical capillary reactor. So you need multiple CSTRs to get to that equivalent residence time distribution. If we're talking about cascading reactions, not cascading, telescoping reactions, which I think is just so I don't misinterpret the question. If you're optimizing conditions with one flow reactor, that's pretty straightforward. If you're doing a 2-step reaction, that gets a bit more complicated. It just takes optimization at each step. So it's, if you're doing telescoped chemistry, so when you're flowing from one flow reactor to the next, it's easier to optimize each of those steps in isolation and then link them together. It's just time and effort.
Great, thank you. Okay, so that's the last of our questions in the Q&A, and we are rapidly approaching the 1 hour mark. So unless anybody has anything else they'd like to add in at this point, I think we will thank everyone for joining us and let you get on with your day.
Yeah, so I just want to say thank you everyone for your time this morning. Hope this has been helpful. I know some people can be shy, even though it's faceless, to put a question down in the chat. If you've got further questions, then please drop us a line, and we're here to help. So thanks very much. We'll see you next time.